All right. This is an evaluation and comparison of open source deep learning platforms. And the business problem we are trying to solve is the benefit of use for each of the two major open source learning platforms, PyTorch and TensorFlow, and to evaluate different options for deep learning on the Cypher-10 dataset. The modeling is done The modeling being done is the classification of images into different categories and predicting which class an image would fall into. We will learn the differences, any advantages or disadvantages, and approaches for implementation for each of the learning platforms by creating 4 models for each framework. The criteria for evaluation we have is subjective to this dataset and narrows down to accuracy. Whatever conclusion we reach on the most effective platform for this dataset likely will change on data with different sizes, different images, and on using different processing architecture. The goal is both to learn the basics behind each platform and conclude which is the best for this data on this machine. We will solve this question with the comparison of the platforms using 4 models, each with different levels and different epochs. The dataset we are using is the Cypher-10 dataset, which consists of 60,000 32 by 32 pixel color images separated into 10 classes with 6,000 images per class, so it's a very balanced dataset. There are 50,000 training images and 10,000 test images, and the different classes are airplanes, automobiles, birds, cats, deer, dogs, frogs, horses, ships, and trucks. And here you can see us loading the dataset using TensorFlow and separating it into training and test sets, both for the images and the labels.
Okay, and for exploratory data analysis, we started off by showing the shape of the data, so we can see that we have 50,000 in the train and 10,000 in the test. And then along with the shape are the matrices for each of the pictures. So 32 is the 32 by 32 matrix of the images. And the 3 is the 3 indices of the RGB table. So red, green, and blue, and each side one of those matrices. So each RGB matrix is inside a 32 by 32, and it corresponds to a pixel, and then therefore we can display the colors of the images based on what's in the table. So then we check for any missing values, which there aren't any. So we can go ahead and proceed with the data. Next, we printed off 25 sample images, and we also printed off the category that it's corresponded with. So we can see that the classes and the images, we can see the class right below each image. So for example, the top left image is a frog, and we listed off the class as the frog, so that is correct. So we are here making sure that each of the images corresponds with the correct classes. So if you look through each one, we can see, for example, automobile, horse, bird, ship, truck. We can see each of these correspond correctly. So we can verify that the training data is correct for these random sample images, so we can assume that they're correct for the entire data set. Next, we printed off the matrix of the RGB values for the very first image in the data set, which is the frog that we saw above. We can see here that it's really shrunk down, but it's a 32 by 32 matrix. You can see there's 32 arrays, and then inside each array is 32 more arrays consisting of 3 numbers that are 0 to 255 that correspond to an RGB value. Next, we showed the distribution of each class in both the training data and the testing data. We can see here that it is balanced across each of the classes. So each class has has exactly 5,000 in the training data, and each class in the testing data has exactly 1,000 images. We can see below the reference and the indices for each of the classes. If they were different, they would matter, but in this situation, since they're all the same, it doesn't matter really what each one is because they're equal.
All right, and moving on to the models, we will be creating multiple models with different levels of complexity. A more complex model will translate to a higher number of layers in the neural network, and vice versa is true. Each of the models will be run using both the PyTorch and TensorFlow frameworks, and the accuracies reported from each framework will be compared. The types of layers we will use are the convolution layer, which will detect features in images using channels. For example, 64 channels will detect 64 features in the images. We will use the ReLU activation function, which will threshold all the features to be greater than or equal to 0. And we will use the pool layer as well to reduce dimensions of images. So the first structure of the model, the structure of the first model will be a convolution layer, a pool layer, a convolution layer, a pool layer, and a third convolution layer followed by the linear output layer. And then here you can see loading the data set using PyTorch and separating into test and training sets. It's slightly more simple and straightforward using TensorFlow, but both frameworks, it's very basic under a few lines to load the data set and separate that out. And here is the class in PyTorch to build the neural network. You can see each of the layers being built and specifying channels, the number of channels for each layer, and range. And then here we loop through each epoch to loop over the data set multiple times to build the model. And the output for each epoch layer is output here. And the accuracy we ended up with using PyTorch was 72% with that first model. And then moving on to TensorFlow, using the same structure model, we first had to standardize the image data. And then you can see this was all the model building we had to do in TensorFlow. So it's comparably shorter and more straightforward in TensorFlow. And then the end result was a very comparable 71% accuracy on the data set. And down here, you can see the validation accuracy climbing well with the test accuracy for each epoch as we go through the loop. And then looking at the network structure, between PyTorch and TensorFlow, there are almost identical values for the output shapes and the number of parameters being used for each layer. The main difference being that PyTorch will count the ReLU activation function as its own layer, whereas TensorFlow will just lump that in with the convolution layer itself. Moving on to the second model, it's a similar structure except there's only one pool function in the middle surrounded by convolution functions on either side, and ending again with the linear output function. Again, we can see here it's a similar number of layers, but we are using different numbers of channels for this model. And looping around again, the end result for this one was a lower accuracy on PyTorch for 66% on the data set. And for TensorFlow, we achieved a similar result at 67%. So both frameworks performed worse using this model. But again, we see a similar performance of the accuracy and validation accuracy just for TensorFlow.
For the third model, we started off with the same format again, except we increased the number of layers and channel size. So the structure is nearly equivalent to the previous model, except as you can see, we increased the number of layers and channels. And then continuing on, we ran through the epochs. And then we got an accuracy of 75% with this model in PyTorch, which is significantly better than the first, or better than the second, and then a little bit better than the first one, but is better than both of them. For TensorFlow in Model 3, as you can see, it is nice and simple for this as well, even with the increased layers and the increased channel size. But we continued and got an accuracy of 71%, which is less than the PyTorch, but I think one of the best for TensorFlow we have gotten so far. Almost equivalent to the first model.
So for model 4, we increase the number of layers, increase the size of the channels, and introduce this method called batch normalization. From my understanding, batch normalization is used to make the neural network faster and more stable by standardizing the inputs to a layer. So in both PyTorch and TensorFlow, between every layer that is created, we introduce this batch normalization process. On PyTorch, to do that, we use this method called batch norm 2D. And on TensorFlow, the name of the method is just batch normalization. Model 4 follows a similar setup on both PyTorch and TensorFlow, like we've been trying to do with all the 3 previous models. And on both frameworks, the accuracy report was around 81%. So onto our results and conclusions. Models 1 and 2 are very simple, but as you can see, model 1 performs slightly better because of the size of the channels used, even though it had one less layer in the neural network compared to model 2. Model 3 adds more layers, and we can see a similar increase in accuracy on both frameworks, with PyTorch performing a little bit better. Model 4 is the one that achieves the highest accuracy of the models that we tested. And it does that by increasing the number of layers used a lot. Compared to model 3, from 16, we went to 26. And also because of the use of the batch normalization process. Batch normalization is supposed to make the training faster, but while training both frameworks on model 4, the process took about 3 hours. So that's not really that fast. It's worth noting that all models that were tested in this project, they were trained using an epoch value of 10. If we were to increase the epoch value, the training process would probably take much longer. So overall, in my personal opinion, I think PyTorch is slightly better than TensorFlow. It feels more intuitive when you are building the network, giving you the idea that you have a better control of what's being done in the neural network process. Regarding the accuracy, both frameworks have very close results. I think that PyTorch performs slightly better on most of them, but the results are so close that you can't say that one is better than the other. For future improvements, I think it would be beneficial to be able to run these models on a powerful GPU and see if the models are trained faster. This would allow for more complex models to be tested and see if a higher accuracy can be achieved. Another option would be using Google Colab Pro version, which I think costs $10 a month, and it offers access to a more powerful GPU, CPU, and more memory. And lastly, I think it would be very interesting for our project to be able to download images, for example, of a bird from the internet and have the model, whichever model had the highest accuracy, classify the image that was downloaded from the internet and see if the model is capable of either identifying a bird or a different type of image that were used to classify this image, like a sheep or a truck.